Hi, and we're now going to have a look at some more detail about proton spectroscopy. And this picture on the right is a NMR spectroscopy machine for proton spectroscopy, for what it's worth, because you can't see much. It looks like a big tank there, doesn't it? But inside the tank is first liquid nitrogen and then liquid helium, and that's to keep the magnets cool, so we've got a strong magnetic field there. So in today's video we are going to do some more on distinguishing between hydrogen atoms. We started that in the previous video. But we're also going to have a look at peak integration. Integration being the area under the curve. You will have come across that in maths. And lastly, we're going to have a look at spin-spin splitting patterns to look at how many hydrogens are in adjacent groups. Okay, let's start off with distinguishing between hydrogen atoms. And the first thing we want to do is pull up our chart, our table, which gives us the chemical shifts for the hydrogens in all those different groups. Okay, so let's look again at ethanol. Ethanol. Okay, so ethanol, as you know, looks like this. So we've got 4 hydrogens in ethanol, and what we can do is we can see that this hydrogen here that I'm ringing in red is going to be in a different chemical environment to the other hydrogens, because the electrons in the bond are going to be much more drawn towards the carbon, because carbon's lost a few electrons, well, electron density toward oxygen. Okay, so this hydrogen here is going to be less shielded than the other carbons, the other hydrogens. These hydrogens here, the 3 hydrogens on the methyl group, first thing we can say is they're chemically equivalent. Chemically equivalent. And that means that they're going to appear on the same peak. So what we would expect here is one peak for those hydrogens that we've expressed in green, and another peak for the hydrogen that is connected to the carbonyl carbon. So why don't we just draw the spectrum that we might expect from ethanol. I'm just going to draw a small chart because I want to do another molecule as well. So we've got our chemical shift, which is our x-axis, and we're going to call that sigma, and we're going to have that go from 0 to 10, and this is our absorption. Some people spell absorption with a P. And so we've got the red hydrogen to work out first. So the red hydrogen, I'm going to circle on this chart here, is going to be connected to a carbon that is double bonded to an oxygen. So I'm going to circle this hydrogen here. So it's connected to a carbon that is, that's wrong. So the hydrogen that's connected to a carbon that's connected to a double bond oxygen is this hydrogen here near the bottom, so that's quite unshielded, and therefore the chemical shift is quite high. You can see it's given there between 9 and 10. So let's draw a little absorption peak there for that hydrogen we've put in red. Okay, now looking at the hydrogens that we've circled in green. They are connected, they are part of a methyl group that is then connected to a carbonyl carbon. And so this group here is a methyl group that is connected to a carbonyl carbon. So there it is, and we can see the chemical shift there is 2.1 to 2.6. So let's say that's 2 there. So we want it just more than 2, so we're going to have a peak here, and I'm going to draw that bigger. I'm going to draw that taller there because the 3 hydrogens in that chemically equivalent group of hydrogens. So that it gives us a taller peak. So that would be the pattern that we'd see for ethanol. Let's do another molecule. Let's do propanone. Propanone. The first thing we can do is we can draw out propanone. 3 carbons. And it's a ketone, so the carbonyl carbon needs a carbon on either side. So this one has to be the carbonyl carbon, which means we've got 3 methyl groups here with hydrogens on the bonds, like so. So there's our propanone molecule, and what we can do is we can see that all 6 hydrogens, even though they're in 2 different methyl groups, are in chemically equivalent, are called chemically equivalent. So these 3 you can see are chemically equivalent, right? So the same amount of shielding as those 3. Right, so they're all chemically equivalent hydrogens appear on the same peak. So we're just going to have 1 peak for propanone. So if we did our spectrum there, we would have, I'll just say ab for absorption, and of course most of the chemical shifts or the frequencies are going to be 0, but we are going to have 1 peak this time, like we've said, and let's find that on the table. That is going to be this one here. So let me do that in red rather. So that's going to be those carbons, those hydrogens there that are on a carbon that is next to a carbonyl carbon, or a carbonyl group. And you can see that's 2.1 to 2.6. So if we scaled that, let's say that was 0, and that was 2, that was 10, right? You're going to have a peak just more than 2, right? And it's going to be a big peak because there's 6 hydrogens there. So we will draw it like that. Like so. And so now we've distinguished between hydrogens, or in fact noted that chemically equivalent hydrogens all appear on the same peak. So if the chemical shift of a peak tells us the functional group that the hydrogens are in, then what we can do is we can also tell some more information from the height of that peak, or in fact the area under the curve of that peak. And so the peak integration, right? So the integration is, as in maths, which is the area under the curve. Area under the curve. And that tells us the number of hydrogen nuclei in that particular group. So what we can do is we can have a look at an example. Let's go back to our ethanol. So let's quickly draw it out. So we've got a carbon, like so. So we've got 3 chemically equivalent hydrogens on the methyl group and 1 hydrogen on the carbonyl carbon. And let's quickly draw our curve. So we have, let's again do it in red for this one. So we're going to have that one there at just less than 10, and we're going to have, let's do it in green, these 3 here. I'm going to go there, just more than 2. And we could even have a table. Sometimes you might even be given a table instead of a graph. So the table might look something like this, where you'd have your chemical shift at 2.3 and 9.8, say, and then your integration ratio. Note that word ratio there, because it's not, we're not always given nice clean numbers. So we would have a 3 and a 1 there, and that corresponds to the height. So you might even see it on on the spectrum looking like so, and that tells you that there are 3 hydrogens here and 1 hydrogen in that group there, which corresponds to what we know about the molecule. There's 1 hydrogen attached to the carbonyl carbon and 3 hydrogens in the methyl group attached to that carbonyl carbon. So then you could work out that this is a CH3 group and this is a hydrogen on its own attached to a carbonyl carbon. Just to be complete, you will see some questions where they give you crazy numbers. So, for example, you might be given this as 0.33 and 1, for example, and that's why I wanted you to notice that word ratio there, because you can't have 0.33 of a proton. So what you do is you multiply that up to 1. So you multiply the smallest number up to 1, just like you do for empirical formulas. So you divide it by 0.33 and multiply it up to 1. Do the same for 1. 1 divided by 0.33 is going to be 3. And so then you get your numbers of hydrogen atoms that way. But either way, you get in the end 1 hydrogen attached to the carbonyl carbon and 3 hydrogens in the methyl group that is attached to the carbonyl carbon. Okay, that's peak integration. This actually involves looking at low resolution spectra. All right, so let's just write that out. This is for low resolution spectra. And as that would imply, you also get high resolution spectra. And when we're going to have a look at high resolution spectra now, but basically our single peaks that we've drawn here are more detailed, and that detail gives us some information about neighbouring hydrogens. And when we use high resolution machines, we get what's called spin-spin splitting patterns, and they tell us what groups the hydrogens are in and what their neighbours are like. So let's use an example. Let's use part of a molecule here that's got a CH2 and a CH3 group adjacent. So we've got a molecule, we've got a H2 group, and then we've got a we've got a CH3 group on the end. So we're looking at the end of a alkane, maybe. And these hydrogens in the methyl group on the end are going to be in a chemically equivalent group, so they're going to form 1 peak. And the 2 hydrogens on the CH2 group there are not chemically equivalent, so they're going to have their own peak. But let's now draw the spectrum for the. This is a low resolution spectrum. And this peak might look like that for the CH3 group. So we're just doing the 3 hydrogens in the methyl group. That peak might look like that in a low resolution machine, but in a high resolution machine you might see this. You might see something like that. So you see it split into 3 peaks. So now we've got 3 peaks, right? And notice we've got 2 hydrogens in the adjacent group. So I just want you to notice that fact, because that's going to lead into a rule. So why is that? Why does it split into peaks? Well, it splits into peaks because these 2 hydrogens in the CH2 group, they're going to interact with the 3 chemically equivalent hydrogens in the methyl group, and they could actually interact in 3 different ways. Let's illustrate it with a diagram. Let's say our magnetic field, the one that we're applying, all right, is coming in this direction. Then those 2 hydrogens could be spinning such that their magnetic fields are both the same and working against the applied magnetic field. Whereas that's one option. You could have another option which is the applied magnetic field is the same, but one of those hydrogens in the CH2 group is spinning one way and spinning in the opposite way to the other one, so that their magnetic fields are opposing each other. And that could happen another way, in that the one hydrogen spins one way and the other hydrogen spins the other way. And it could also happen a fourth way, in that the applied magnetic field is in the same direction as both of the hydrogens. So I think you see that these two are the same. So they are the same, and so the proportion of the proportion of those we can say is 2. And we've got one where both hydrogens oppose the applied magnetic field, and we've got one situation where both hydrogens are parallel with the applied magnetic field. And so that's where our 3 peaks come from. Right, so the first peak, where the hydrogens in adjacent group is going to oppose the applied magnetic field, will result in this little peak here. These two together result in the tall peak, right, and this one here results in the third peak there. And so that's how you get 3 peaks. So that information, the fact that there's 3 peaks on 3 sort of like mini peaks on the peak for the CH3 group, tells us something about the adjacent hydrogens. Right, the adjacent hydrogens being these hydrogens here. It tells us there's a CH2 group next to it. So we'll just go over that again with a simple example. I've got a complicated example in a separate video, but this simple example, let's say we've got a spectrum for a chlorinated alkane. So let's look at a chlorinated alkane. That's all we know, but we're given the spectrum like so, and we've got 3 peaks like so at about 1 point something, and we've got 4 peaks like so at 3 point something. We're given a table to go with it, and the table gives us our shift numbers of 1.2 and 3.4, and it gives us the integration ratio as well of 3 and 2. So I'll just call integration ratio IR, and from that we've got to work out what the molecule is. So let's do that. So let's see what all this information tells us. Well, our integration ratios first, so let's look at our integration ratios first. We know we've got an alkane, so in alkanes we know we've got CH2s and CH3 groups. It's going to have a chlorine on it somewhere. And so we can possibly say that this one is a CH3 and this is a CH2 group, given the fact that we've got 3 hydrogens in one environment and 2 hydrogens in the other environment. If we now have a look at the splitting pattern, we've got 4 peaks here, which means the neighbouring group has got 3 hydrogens, and we've got 3 peaks here, which means the neighbouring group has got 2 hydrogens. So this peak here is going to be our CH3 group, and this peak here is going to be our CH2 group. And then looking at the chemical shift, that's the chemical shift. So we've got our CH3 group has got lower shift than our CH2 group. Our CH2 group has got a high shift, which means that it's de-shielded. Right? So CH2 group is de-shielded, which means it's going to be near to an electronegative element. And hey presto, we've got chlorine in this molecule as well. Okay, so what all that suggests is that the chlorine is next to the CH2 group, because you gathered that from the chemical shift. And we've only got 2 peaks, so that means we've got a CH3 group further away from the chlorine, because it's got the shift there. And hey presto, we've worked out the fact that we've got this molecule here, which is chloroethane. Okay, so let's summarize the splitting patterns into a rule. It's called the N+1 rule. So this is the N+1 rule, and we can put that into words by saying that if there are N+1 peaks, if there are N+1, let's put it in brackets, peaks on the spectrum, then this is caused by N hydrogens on adjacent carbons. So in the previous example, we saw that with this group that I'm underlining in purple here, it had 3 peaks, so there were 2 hydrogens in the other peak, and this peak here had 4 mini peaks, so there were 3 hydrogens in the adjacent group to it. So let's look at a trickier example of the N+1 rule, the splitting of the peaks. And in order to do this, let's use the propane molecule. So propane has 3 carbons, of course, but I'm going to draw the molecule like this. With the middle one in black. Alright, so we got, let's draw 2 black hydrogens and 6 red hydrogens. Okay, so the red hydrogens are chemically equivalent, the black hydrogens are chemically equivalent, so we should have 2 peaks. The integration ratio of the red ones should be 6:2 or 3:1. So let's see what we get. Our spectrum might look like this. Hopefully I can draw it nicely. So we've got our chemical shift. Let's say we've got 0, 1, 2, 3, something like that. And our CH3 groups have 6. CH3 groups are going to be have a chemical shift just less than 1. And that pattern is going to be split. Let's switch to red. So we're going to have this pattern. It's going to be split into 3 because we've got 2 hydrogens in adjacent carbon. Right, so we've got Bosch. So Bosch like that, very badly drawn, sorry about that. But we want that. We also want another peak here where we're going to have peak that looks like that. Okay, so let's put our integration values on. So you might even see this written like this, an integral sign here with a 6 and an integral sign over this peak as a 2. It could actually be 3 and 1, right? You might see it could be 3 and 1 there. The ratios are the same. Let's just let's have a look at our peaks here in slightly more detail. So let me blow this up here. Well, let's just say, instead of blowing it up, let's just say that it's got 7 peaks. All right, so that 7 peaks leads you to know that 7 peaks means that there are 6 hydrogens on neighbouring carbons. That's what that leads you to believe. And we've got here we've got 3 peaks, and that leads you to conclude that there are 2 hydrogens on neighbouring carbons or carbon. Okay, so as you can see, we've got a chemical shift of slightly less than 1. So let's look at this chemical shift here, which is, let's call that 0.9. So you could look up in the table and you could see that's hydrogens in a CH3 group of an alkane. All right, so, and you could look up this peak here, the other peak, the one that we've drawn in black, and you could see that's hydrogens in a CH2 group of an alkane. And so from the integration ratios of 6 to 2, and from the fact that you've got you've got 6 carbons on adjacent hydrogens, you can conclude you've got 2 times CH3 for that peak and 1 times CH2 for that peak, in which case we can then draw our molecule. And so that I think is all we need on the n+1 rule. What you will see in your textbooks is a table like this, similar table to this, which just gives you the names of all of the patterns there. So you call a singlet a single peak, and if it's got 2 peaks, you call it a doublet, etc., right up to a sextet or a septet. In fact, the one that we had here would be off the bottom of this table. It's called a septet. There, so hopefully that's clear. But just before we finish, let's make sure you've understood everything here. So can you distinguish between hydrogen atoms? Can you work out how many hydrogens there are in the groups from peaks? And can you also use the spin-splitting patterns to work out how many hydrogens are in each group? If not, prepare your questions, bring them to class.